Hi, yet another important video from the course Analog Electronic Circuits. Continuation to my previous video. It's a hybrid pi model. Guys, it was derived expression for GM. In my previous video, I have derived expression for GM. It was GM was found out to be IC by VT. Right? It's directly proportional to the collector current and inversely proportional to the volt equivalent temperature. So, the point is, hybrid parameters will be given, the low frequency component values will be given. We have to evaluate the high frequency component values of a transistor, right? So for that we need to consider the hybrid pi model again, how it looks like, guys. It's always common emitter configuration for various reasons, and we have that base over here, and the analysis is with respect to the virtual base B dash. We have that B dash over here, virtual base, which we cannot access, the very center point of the base, and all the capacitances and resistances will be arising with respect to that point, we say. So that resistance between B and B dash, guys, it's RB dash, also known, it has got a name, base spreading resistance. Okay, so we have the output collector over here, let it be over here a bit far, collector, and between base B dash and C we have another resistance RB dash C. That resistance offered by the reverse junction, JC collector junction should be reverse biased, isn't it, when we make use of a transistor as an amplifier, that resistance. And emitter is made common as both to input and output. Here we have that emitter, and that resistance, forward bias junction JE, also gives rise to a resistance RB dash E. Okay, and here we have that VBE, and we have that VB dash E here, and IB flows over here, IB, guys. And what else? Another resistance we have to take it into account, IC, we have IC, and from this very previous one, what did I write down here? VB dash E. With the increase in VB dash E, there will be an increase in IB. Consequently, with the increase in the input current, there will be an increase in the output current, IC, right? In the sense, IC is directly proportional to VBE, IC is directly proportional to VB dash E, sorry, not VB, VB dash E, and from that which we have IC is equal to GM VB dash E. Yeah, we need to look back to this one. We'll have to make use of that expression also, right? And here we have now the resistance which cannot be neglected here. It's RCE, output resistance. And what is that voltage measured over here? It's a VCE. This is the voltage measured across this. We have to show this one. This has to be reflected in the hybrid pi model. This one, IC is equal to GM VB dash, that has to reflect over here. We have IC over here, this one, this here. We have that, what is that? IC, which is equal to GM VB dash E. This is the one. Okay, and some capacitances also comes in between, isn't it? No, guys, here the focus is to evaluate the expressions for all these resistances. Now this RB dash C is known as a feedback resistance, and the reciprocal of this one, RB dash C, 1 by RB dash C, which is GB dash C, is known as a feedback conductance. Why? Because it's existing between output collector and the input B dash, right? And base spreading resistance and input resistance, yeah, we have to derive the expressions for all these resistances, and the reciprocal of the resistances, it will be the conductance. Indirectly, in the exam point of view, it will be asked to evaluate the conductances of a hybrid pi model, or else you may have a numerical. All the H parameters will be given. It will be asked to evaluate the high frequency parameters of a transistor. High frequency parameters, all these parameters. Okay, capacitance, guys, capacitance do exist, but for the time being, it's like evaluating the resistances and conductances. So I'm not drawing the capacitances. Okay, we have CB dash E across over here and CB dash C across over here. Yeah, not focuses on resistances and conductances, so neglecting the capacitances. And here RB dash, another important point to be remembered, which will be made use in the during the analysis, the simplification. This is the RB dash C. RB dash C will be very much higher than RB dash E. If at all we have a equation having RB dash C plus RB dash E, we neglect RB dash E. What is the justification for that? Don't believe unless we have a justification. So why this exists? Why this? How? What is that? How can you say that it is? Yeah, what is the justification for that? RB dash C is the resistance offered by a reverse junction, JC, collector junction. It's always reverse biased, and that resistance offered by the reverse bias junction is very higher when compared to the resistance offered by the forward bias junction. This will be in terms of mega ohms and this will be in terms of kilo ohms, and when we have a sum, we neglect this one. RB dash E is neglected generally in the analysis for the simplification. And on the other hand, the parallel, if we have a parallel combination of this one, if at all we have a parallel combination of this one, this can be neglected. The resultant will be equal to the smaller value resistances, and so parallel combination of this one, RB dash C and RB dash E, the equivalent will be equal to RB dash E. Okay, guys, evaluating, remember first this has to be evaluated, then all the resistances. Okay, so in that case, what is this drop? Guys, this drop. What is this drop? It's a VB dash E. VB dash E is equal to IB RB dash E, right, which gives us that expression for RB dash E. So why IB? We have IB flowing from this side and we have IC flowing from this side. So why only IB? It's a very high resistance, right? It's a very high resistance, and this may restrict. May not, it's not may. This is a very high resistance. Whatever current is flowing through this one, that will be flowing through this side. Okay, and IB, whatever IB after this node, it has to split into this current and this current, but still it's a very high resistance. Current will be flowing through the low resistance when compared to this one, right? Larger, almost all the IB will be flowing through this one. Very little amount of IB will be flowing, part of IB will be flowing through that side, which can be neglected. So in that case, we have VB dash E is equal to IB RB dash E. So guys, from this very expression, VB dash E could be written as IC by GM, isn't it? From here, vary this expression. We need VB dash E, so IC by GM. The transconductance IC by GM is equal to what? RB dash E into IB, right? IB. And what do we have? What is that ratio? So guys, it's IC by IB, here IB, which is equal to RB dash E. Can you remember if this, what is this ratio? From the H parameter model which we have, IC is equal to HFE IB, which can be seen in the hybrid parameter model. So this ratio IC by IB will be equal to HFE. So plugging in that, right? IC by IB into by GM we have, right? GM. So what is this ratio? We have this GM, okay? So what is this ratio? It's RB dash E is equal to this one, HFE by GM, right? For the expression for the RB dash E. How did I get it? VB dash E, from this very expression we have IB, this current IB into RB dash E, right? And from the previous analysis we have IC is equal to GM VB dash E. This value of VB dash E, which is equal to IC by GM, is plugged in over here, this as it is, okay, IC by GM as it is, and here RB dash E will be equal to IC by IB by GM, right, over here. And from the previous knowledge of H parameters, the ratio IC by IB will be equal to HFE, IC by IB is equal to HFE, that's plugged in, and by GM, RB dash E. So what will be the conductance? GB dash E, it's simply the reciprocal of this one, 1 by RB dash E, which is equal to GM by HFE, right? Expressions for the resistance RB dash E and the reciprocal conductance GB dash E. So we'll have to make use of this one. Okay, so I'm writing it over here. Yeah, GM, we have that one. The GM, we'll be having GM beforehand, so that can be plugged in, which I have just erased right now. IC by VT, plugging in all these, there is a small simplification, but RB dash E is found out to be what? HFE by GM. HFE by GM, guys. So whenever we have that product, GM RB dash E, that could be plugged in with HFE. Yeah, we have to do that one. Okay, so what is next? It's a RB dash E. With these values, we can evaluate RB dash C also. First one, this one, next this one, then this maybe, and after this one. Okay, so guys, with it's a feedback. Okay, RB dash C is a feedback. Why? Because feedback resistance. Why? Because it's existing between the output and input. So in order to evaluate this one, feedback part, we have to consider IB is equal to 0, and a small modification in the circuit will help us to understand better. Okay, so with IB is equal to 0, this is for RB dash C, IB is made 0, and then the evaluation is carried out. So guys, a small modification over here, for me to explain it more clearly. So that we have a positive and negative of VC, this point, guys, this point, plus positive and negative of VCE for my convenience. Okay, I am redrawing this for my convenience, and IB is equal to 0, and those components which are parallel to this point, positive and negative of VCE, those components here, this one RC, this one, if you point out over here, RC is in parallel with this one here, this one, RCE is in parallel with this point, What else? GM VB dash E also is in parallel with this one here, this generator. GM VB dash E is also in parallel, this component also is in parallel with this one, and another one, yeah, this point, from this point to this point, this point to this point is also, guys, IB is equal to 0, so we don't have this drop. Okay, IB is equal to 0, we don't have this drop, and yeah, we don't have this drop, so we don't have this, we don't need to consider that one. So from this point to this point is also in shunt with VC. What is that? We have RB dash C, the series combination, and here RB dash E with what is that voltage? VB dash E over here. Okay, this one, this combination. Okay, so guys, for another simplification, for better understanding, I am erasing this one. The main focus is to evaluate RB dash C, so considering this one. Now here we have VCE plus VCE over, making use of potential divider rule to evaluate, what is that equation that has to be written for VB dash E according to potential divider rule? So VB dash E will be equal to that voltage measured across this one according to potential divider rule. VB dash E will be equal to that resistance RB dash E into VCE by total resistance, isn't it? What is that? RB dash E plus RB dash C, right? So this is the modification, and this is the expression we want. Okay, so guys, and over here we have that expression VB dash E by VCE, which is equal to RB dash E by RB dash C plus RB dash E. Okay, so guys, that one, this is another hybrid parameter. What is that? So guys, what did we have? It's the second equation in hybrid parameters, I2 is equal to H21 I1 plus H22 V2. Okay, or else another one, it's a V1 is equal to H11 I1 plus H12 V2 from H parameters. Okay, so guys, with IB is equal to 0, in the sense I1 is equal to 0, with that assumption, what do we have? V1 by V2, which is equal to H12, which is equal to, what is this I guess it's a HRE, right? HRE of a hybrid in H12 is nothing but HRE representation in common emitter configuration, right? So this is the input voltage and this is the output voltage. We have input voltage and we have output voltage. So if you are not happy with this one, there is another assumption. Input, this VBE is equal to VB dash E. We can write that one. This VBE is equal to VB dash E. Why? Because we made sure that no current is flowing through this resistance. Okay, here watch carefully for this justification for this equation. What is that is, resistance, we have VB on this side and VB dash E on either side of this resistance. Here it's this resistance. Okay, so according to that theory, when the current through the resistance is 0, that means the voltage drop on either side of the resistances are equal, right? So how to write that expression? If at all we have IB, how to write that expression? It's a VBE minus VB dash E by RBB dash, isn't it? So when IB will be 0, these two voltages are equal, and then IB will be 0. So IB is 0, so these two voltages are equal. Okay, so in that case, okay, it may be HRE may be VBE by VCE, actual one, but VBE is equal to VB dash E according to this one. IB is equal to 0, so resistance, the drop on either side of the resistance are equal. So in that case, okay, so here, and now this ratio will be equal to what? Which is equal to this ratio, reverse voltage gain, HRE, right? This one. And when we cross multiply these two, what is that? What do we have? It's a HRE RB dash C plus HRE RB dash E, which is equal to RB dash E. Okay, so this one, this is cross, I need this place. Okay, so this one, so this is the simplification, and HRE RB dash C, this is suffix. Okay, I may go wrong, it's a H suffix RE RB dash C is equal to, pulling this term to that side and taking out what do we, hold on, RB dash E minus HRE RB dash E. Okay, so what do we have? Taking out RB dash E as common, 1 minus HRE by HRE gives us RB dash C. Okay, so guys, generally HRE is very much smaller in quantity when compared to 1. It will be in the order of something into 10 raised to minus 4, in the sense 0.000 like that. Okay, so generally HRE when compared to 1, it will be very much lesser, and so in this one, in this difference, HRE can be neglected, this one. Okay, and this is the expression for RB dash C, and GB dash C will be the reciprocal HRE by RB dash E. Okay, so this is the expression for RB dash C and GB dash E. The feedback, they call it the feedback conductance, RB, this one, the feedback conductance. What is that? RB dash C, we got to be, what is that? RB dash E by HRE. Guys, from here itself we can say that this value is very high, we'll be having RB dash E, which is divided by HRA, which is a very less value, 10 raised to minus 4. Going up, that will be 10 raised to 4, and then that gives RB dash C is very much higher than compared to RB dash E. Okay, so guys, what was evaluated? RB dash E, yeah, we have this RB dash E. The feedback conductance GB dash C. If we have RB dash C, it's known that GB dash C we have, right? And we need to evaluate the base spreading resistance. That is evaluated making use of another assumption that input resistance making Vc is equal to 0. Making Vc is equal to 0, no current from this side. Vc is when VCE is equal to 0, we don't have all this one. Okay, so this becomes invalid, and we can consider this one. VBE is equal to IB into RB dash plus RB dash E, right? So VBE by IB, which is equal to HIE from hybrid parameter knowledge, HIE, which is equal, this ratio is HIE, which is equal to RB dash plus RB dash E, right? So guys, we are in search of RB dash, which is equal to HIE minus RB dash E. Okay, so this is expression for the base spreading resistance RB dash. Okay, so here, so what is that expression for RB dash? It's a HIE minus RB dash E. So here, last but not least, the expression for RCE. What is that expression for? Let's see if what is that expression for RCE? It's a output resistance. So output impedance is calculated making use of IB is equal to 0 again. IB is equal to 0. So we don't have this drop. We don't have this drop. And yeah, we don't have this drop. Okay, so IB is equal to 0. And guys, so what will be IC? Writing that expression for IC over here. IC, writing that expression for IC. Right? Watch very carefully. Here, generally there is a bit confusion over here. So, how to write this resistance? I mean, how to write this current? This one. How to write? How to write this current? This current. This one. This current. It's a VCE by RCE, isn't it? This current plus this current GMV B dash E, this current. Okay, current through this one VCE by RC, and this is a current GMV B dash E plus how to write that current through this one. We have done with this one, this current. So here it's again how to write the current through this series combination. It's a VCE by RB dash C plus RB dash E. Okay, so guys, that's one. And from here, from this arrangement, we have VB dash E, isn't it? That VB dash E could be rewritten in another form. What is that? Once again, according to potential divider rule, this IC is equal to VCE by RCE plus GM, guys, GM, and this, it's a VCE into RB dash E by RB dash E plus RB dash C. Okay, according to potential divider rule previously, which I have rewritten again, plus VCE by RB dash C plus RB dash E. Okay, so guys, something is common in all the three expressions over here. right? Something is common, it's a VCE, VC and VC, taking that common and pulling that to the LHS. So we have IC by VCE is equal to 1 by RCE plus. So guys, if here in the absence of VCE, dragged VCE to this side, so GM RB dash E could be plugged in with something else. The product GM RB dash E, GM RB dash E could be plugged in with HFE for simplification. Okay, this product GM RB dash E, again I repeat, GM, this GM into RB dash E, that will be HFE. If we carry this to that side, GM RB dash E will be equal to HFE. This one, this product is equal to HFE by RB dash E plus RB dash C. What are we in search of? Guys, I guess we are in search of this one, isn't it? Yeah, RCE plus, we don't have that VC anymore, it's a 1 by RB dash C plus RB dash E. Okay, so in that case, guys, this ratio is equal to some other hybrid parameter, this one IC by VCE. If I am not wrong, this analysis is carried out making use of IB is equal to 0, I1 is equal to 0, right? So what do we have? I2 is equal to H21 I1 plus H22 V2, isn't it? So making use of that point again, IB is equal to 0, in the sense I1 equal to 0, it's a I2 by V2 is equal to H22. So this is nothing but HOE in the common emitter configuration. So I2 is IC and V2 is VCE. So this one, this ratio is equal to, now this entire, this ratio is equal to HOE. Okay, from the knowledge of hybrid parameters, this one, right? So here HOE will be equal to, guys, 1 by RC, 1 by the reciprocal, it's GCE plus HFE. And here I have told you, if you have this combination, this is very higher, this one, this is very larger when compared to this one. So this could be neglected over here. Okay, even in this case, this could be neglected, RB dash A, when we have this combination. Okay, so what do we have? It's a HFE and GB dash C plus GB dash C. Okay, GCE is equal to, and this is what, GCE plus 1 plus HFE GB dash C, which is equal to HOE. So we are in search of the output conductance GCE, which is equal to 1 by RCE, which is equal to what? Which is entirely equal to what is that? HOE minus, guys, HFE is very high when compared to this one. So HFE, neglecting one over here, it's a GB dash C. Okay, expression for GC, which is equal to the reciprocal of 1 by RC, which is equal to that. Right? So this is how we evaluate all the 4 parameters of a hybrid pi model. And you have numericals. It's a reminder, guys, you will have a numerical based on what type of numerical. All the H parameters, HFE, HIE, HRE, everything will be given. You will be asked to evaluate the values of the hybrid pi parameters. Right? So this is the equation. Hope you understood. Thanks for watching.